The aim of this course is to explain the fundamental principles of metrology for the characterization of building envelope materials. This course was prepared by Dr. Maria Teresa Calcagni and Professor John Marco Revel from Università Politecnica del Marche, leader of Work Package 5 in the framework of the European project Exploit 4 Inomat. Here you can find a quick overview on the topic of the course. We will start with an introduction to metrology. Then we will cover the topic concerning metrology for characterization of materials. Consequently, we will focus on characterization of building envelopes materials. Finally, we will present the metrology service for Exploit 4 Inomat. In these introductory slides, will be outlined the fundamental purpose of metrology within modern engineering and scientific practice. Metrology provides the framework needed to transform raw measurement data into meaningful information that supports decision-making, process optimization, and quality assurance. The discipline ensures that measurements are reliable, traceable, and comparable, forming the basis of consistent industrial performance and scientific rigor. Metrology can be defined as the science of measurement and its applications. It establishes the methods, units, and standards required to produce measurements that are accurate and reproducible. The key idea is that measurements should not merely be numerical outputs, but verified quantities supported by calibrated instruments, uncertainty analysis, and traceability to recognized standards. This ensures confidence in data, which is essential for industrial quality, safety, and compliance with regulations. From an industrial perspective, metrology generates substantial strategic value. First, it enhances product quality by reducing variability, rework, and waste. Second, it increases confidence, ensuring that products perform as expected in real conditions. Third, it supports regulatory compliance, enabling companies to meet international norms such as ISO standards and participate in global markets. Finally, metrology improves efficiency by enabling statistical process control and data-driven optimization of manufacturing operations. With the rise of digitalization, metrology is evolving into Metrology 4.0. This paradigm integrates digital twins, enabling the real-time creation of virtual replicas of physical systems. Automation allows inline measurements without human intervention, significantly increasing throughput and consistency. Furthermore, big data and advanced analytics support predictive assessment of production performance and early detection of anomalies, marking a shift from reactive to proactive quality management. Three important aspects to be considered for the quality inspection are: traceability. Every measurement must be linked to reliable international standards. Accreditation. The guarantee that those performing the measurements have the technical expertise to do so. Standardization. Common language, ISO ASTM standards, for global trade. A measuring instrument can be modeled mathematically to describe its input or output behavior. Its characteristics include sensitivity, linearity, accuracy, and susceptibility to disturbances. Static and dynamic calibration procedures are used to determine these characteristics. By understanding the instrument model, we can evaluate performance under different conditions and establish its suitability for specific measurement tasks. Static calibration aims to determine the relationship between a controlled input and the corresponding output of a measurement system under quasi-steady conditions. The procedure uses a reference instrument with an uncertainty at least one order of magnitude lower than that of the instrument to be calibrated. Static calibration provides essential parameters such as sensitivity, calibration coefficients, linearity error, accuracy, and disturbance effects such as temperature influences. The spring dynamometer illustrates how temperature can act as both a modifying and interfering input. Variations in temperature change the spring constant, modifying the input or output relation, and cause thermal expansion, producing output even with zero applied force. The calibration curve is often obtained using least squares interpolation to determine the linear coefficients and associated uncertainties, including sensitivity drift and zero drift. The objective is to determine the best fit linear relationship between input and output and quantify the uncertainty of this approximation. This includes estimating the uncertainty in the measured quantity using the calibrated instrument. Understanding these uncertainties is essential to ensure that measurement results remain within acceptable tolerance limits. Dynamic calibration is required when the input varies over time according to a known law. The dynamic behavior of the measurement system is modeled by a linear differential equation with constant coefficients. By solving this equation, we determine the operational transfer function, which describes how the system responds to time-varying inputs. The general model is a linear differential equation with constant coefficients. Qo, Qi are functions of time. Ai and Bi are real constants characteristic of the system. Note that for the input Qi, the output Qo is given by the solution of the differential equation. Zero-order instruments exhibit an instantaneous response, producing an output proportional to the input without delay, distortion, or phase shift. The operational transfer function reduces to a constant gain. An example is the ideal potentiometer used at low frequencies, where inertia and friction effects are negligible. In such conditions, the instrument behaves as an ideal measurement device. First-order systems include instruments whose differential equation contains terms up to the first order. A common example is the bulb thermometer, where the thermal expansion of fluid in the capillary determines the output. The response depends on the time constant, which describes how quickly the instrument reacts to temperature changes. Mechanical delays due to fluid inertia are typically neglected for simplicity. Second-order instruments follow a differential equation that includes up to second-order terms. Typical examples include weighing scales, where mass, spring stiffness, and viscous damping influence the dynamic response. Key parameters include natural frequency, damping ratio, and static sensitivity. Designing such instruments requires balancing dynamic stability with adequate sensitivity. To obtain a flat response up to high frequencies, the natural frequency of the system should be high. To have a rigid spring, the constant decreases static sensitivity, and you have a small mass. Now the focus is on the usage of metrology for characterization of materials. Material characterization provides insight into the relationships between structure, properties, and performance. It underpins innovation, supports failure analysis, and ensures quality control of raw materials. Understanding physical, chemical, and mechanical properties allows engineers to optimize materials for specific applications. Spectrophotometry measures how much light a sample absorbs at specific wavelengths, allowing determination of chemical composition and concentration. A spectrophotometer emits light onto a sample, and a detector measures the transmitted, absorbed, or reflected portion. This technique is fundamental for analyzing both biological and chemical substances in research and industrial contexts. Mechanical tests simulate real operating conditions to assess parameters such as tensile strength, hardness, and resilience. These tests verify that materials can withstand expected loads and environmental conditions, ensuring reliability and safety. Such evaluations are essential in building envelope materials, where durability and performance critically impact long-term efficiency. At this stage it is important to understand why metrology is fundamental for the characterization of building envelopes materials. The building envelope functions as the protective skin of a structure. Its characterization is vital for optimizing energy efficiency, acoustic and thermal comfort, and resistance to environmental agents. Accurate metrological analysis enables improved design and long-term monitoring of material performance. Advanced technologies such as drones equipped with thermal cameras facilitate large-scale facade inspections. 3D modeling enables the creation of digital twins that support predictive maintenance. These innovations allow early detection of deterioration, reducing maintenance costs and preventing structural damage. Metrology service was critical for the Exploit 4 INOMAT European project. Within the Exploit 4 INOMAT project, metrology services include characterization, interlaboratory testing, and the development of new measurement protocols. These activities ensure that innovative materials meet required standards and that results obtained by different laboratories are reliable and comparable. Water vapor permeability is crucial for evaluating breathable membranes in construction. Following the UNI EN 12086 standard, specimens are conditioned under controlled temperature and humidity, and vapor transmission rates are measured. This ensures accurate assessment of material performance in real environmental conditions. UNIV-PM role was to characterize the cement-free panel material made by agrowaste for the water vapor permeability. On the same type of material, FALU performed acoustic absorbance and USTUT performed reaction to fire. In this framework, we will focus on the explanation of the procedure of the water vapor permeability. This test was made following a methodology, using appropriate containers for containing the samples during the tests. Salts of potassium nitrate were used for the solution, and finally the assembly of specimen and solution was made using the containers. The assembly was inserted in the climatic chamber for the test, and the assembly was weighted every day. Shows the results of the weight loss of 2 specimens during the days. Round-robin tests involve multiple laboratories analyzing the same specimens to evaluate reproducibility and validate measurement methods. This is essential for establishing standardized protocols and ensuring consistency across partners in the Exploit 4 INOMAT project. Total solar reflectance, TSR, quantifies how much solar radiation a material reflects. Testing follows ASTM E903 and G173_03 standards, while repeatability and reproducibility are evaluated using ASTM E69199. This round-robin was conducted by UNIV-PM, Kansai Alton, and NTUA. TSR is especially important for coatings designed to reduce heat absorption in building envelopes. In this slide is reported the measurement performed on the steel specimens coated with polymeric particles. In this slide are reported 2 graphs representing on the left the total solar reflectance at different concentration of polymer in the paint for different spectral ranges, on the right the absolute reflectance of the paint at each concentration of particles. The project includes defining measurement protocols for mock-ups in Lavrion to assess innovative paints and bricks. This involves selecting sensors, defining procedures, and establishing monitoring strategies aligned with performance requirements. I thank the audience for their attention and invite for further discussion at the email address shared in the slide.